Today's topics are going to focus on algorithmic bias and stable matchings. Before we get into any particularly detailed material, I want to give some disclaimers. First off, I should say that algorithmic fairness and bias in algorithms are really rich and complex research areas, something that a lot of researchers are exploring right now. Today, we are only covering the tip of a teeny tiny part of the iceberg that is this research area, in which there are a lot of problems that we are still working on solving or may never be solved. My priorities today are some definitions, a little bit of classic graph problem work, and room to potentially have future discussion, but we might not solve any problems that you'd be hoping to find solutions for. I also want to warn you that some of the topics we'll talk about today relate to systemic racism. If that's something that makes you uncomfortable, or that you're going to need to take a minute to process, please take the time that you need to do so. Two questions we might ask about an algorithm in the broad space of what we're discussing today are what makes an algorithm optimal and what makes an algorithm fair. I'll say a problem solution is optimal if it satisfies some kind of objective for that problem. For instance, we're maximizing or minimizing some value, or we're avoiding all conflict in a particular setting, or so on. That based upon the constraints and things that we want to have in our problem, we have done as well as we possibly could. We describe an algorithm as optimal if, for that problem, the solutions it produces will satisfy the objective that we have, that they won't violate any of our constraints, and that they'll get the best value we possibly can within those constraints. Let's talk about an example problem. This problem is called stable matching. I'm going to use the example of horses and jockeys. Stable matching. Get it? All right. We're going to set up a problem where we have 4 different horses and 4 different jockeys to ride them. In my particular version of the universe, I like to imagine that these horses are sentient and get to help pick who their jockeys are. However, if you don't prefer whimsy, you're welcome to imagine that in this case, jockeys are trying to pick which horses they prefer to ride, whereas barns or stables might be interested in selecting particular jockeys for their horses. We're going to represent these preferences as ordered lists for each of the horses and for each of the jockeys. So for instance, we might establish that horse number 1 likes jockey A the best, followed by B, then D, then C. Every single horse and every single jockey is going to have an ordered list of all of the elements in the other group. Every horse will list every single other jockey in sorted order for their preferences from most liked to least liked, and vice versa. We'll describe a stable matching as a matching of each horse to exactly one jockey and each jockey to exactly one horse, such that no pair of horse and jockey would prefer each other to their current assignments. In this case, like maximum bipartite matching, we are assuming that every single horse will only be assigned exactly one jockey, every single jockey will be assigned exactly one horse, so nothing will be unassigned and nothing will be assigned to more than one at the end of this problem. An example matching we could set up would pair, for instance, horse 1 to jockey B, horse 2 to jockey A, horse 3 to jockey C, and horse 4 to jockey D. We could ask, is this stable? Can we establish that there's no pair of horse and jockey, such that that horse would prefer the jockey and the jockey would prefer the horse, with respect to the ones that they're currently paired with? The answer in this case is no, this isn't a stable matching. We can spot that if we look at horse number 3 and jockey A, both of them actually list each other in their preference lists higher than the horse and jockey respectively they're currently paired with. In this case, they would rather be paired together, so this particular pair of 3 and A represents an instability in the graph. If we matched these two instead and adjusted the matching as follows, 1 is paired to B, 2 is paired to C, 3 is paired to A, and 4 is paired to D, we see that this is stable. While not every single horse is necessarily paired to their top choice, every single other choice that they would be interested in being paired to above theirs is already paired to another horse that they like better. In this case, for instance, jockey A still prefers horse number 3 to horse number 1, even if horse number 1 would prefer jockey A to jockey B. How do we find these stable matchings? An algorithm from 2 graph theorists, Gale and Shapley, helps answer this question. In 1962, this problem was originally stated as the college admissions and stability of marriage problem, and this might seem like a weird thing to do. But when I talk about the stable matching problem, I'm talking about what people would often conventionally refer to as the stable marriage problem, which is about the most Jane Austen thing you've ever heard of. The version of the stable marriage problem that you would imagine, instead of having horses and jockeys, has proposers, who in their particular convention are single men in possession of a good fortune, and responders as the wives that they would want in this formulation. Now, I prefer horses to heteronormativity, so I'm using this construction instead, but if you ever hear people talking about stable marriage, they are talking about this same problem. So why do we talk about this problem? Well, in addition to work done by David Gale and Lloyd Shapley on this, Alvin Roth also contributed to this problem, and the combination of this problem and the corresponding solution was applied to a lot of real-world scenarios. The highest profile version of this that people usually think about is called the MATCH, or the National Resident Matching Program. The National Resident Matching Program is used to match hospital residents, people who are finishing their medical program, with residencies that are available at different hospitals. People will express their preference for which hospitals they would be assigned, and hospitals will represent their preferences for which candidates they'd like to have for their residencies. Matching these represents an interesting kind of matching problem that can be solved with an algorithm very similar to the classic Gale-Shapley algorithm I'm going to show you today. This algorithm can also be used in the case of assigning students to schools or assigning organ donors to recipients. Let's walk through the algorithm. The Gale-Shapley algorithm has the following pieces. We'll start by setting up our list of proposers and our list of responders, and their corresponding lists of preferences. Initially, we're going to, as we keep track of which proposers and responders are matched and which are unmatched, mark every single proposer as unmatched. Then, while there is an unmatched proposer, we're going to do the following. We'll have them propose to the first person in their list of preferences, going from most preferred to least preferred, that they haven't been rejected by yet. In this case, nobody's rejected anyone else yet, so we're going to start by having our first horse ask our first jockey, jockey A, whether they'd be willing to be a jockey. The responders policy is going to be, if there's not already a better proposer that they're matched to, they'll accept the proposal, discarding any prior proposal if they happen to have one. In this case, responder A hasn't been matched to any horse yet, and so the jockey will gladly accept horse 1's proposal. We're going to continue this process to continue to do the matching that we need to do until every single horse is assigned to one jockey. First, we want to find an unmatched proposer. The next unmatched proposer in our list appears to be horse number 2, and horse number 2 is going to do its next best proposal. It happens to be the case that that proposal is to jockey A, the same as what horse 1 proposed to. So horse 2 will propose to jockey A to be matched, and jockey A actually looks at their preferences and sees that indeed they prefer horse 2 to horse 1, so they'll accept that proposal. Unfortunately, that means they'll discard the proposal that they had before, leaving horse number 1 no longer matched again. We'll continue this process. We find an unmatched proposer again. This time it's horse number 3. We'll have them propose. Again, they're going to propose to the top person that hasn't rejected them yet in their list. That's jockey A. And jockey A has gotten yet another upgrade. So, because this is an improvement, jockey A will accept this offer and again abandon its previous proposal. You can see that in this process, it's natural that jockeys are always going to have the quality of the particular proposer they're matched to improve over the course of the algorithm. They'll never reject a particular pair for an option that would be worse. Continuing this process on, we'll look at the next horse right here. Horse number 4 prefers jockey D the most, so that matching is pretty easy. Jockey D will accept that. Next, we'll go back to horse number 1. And horse number 1's next choice on the list, having already visited A, will be jockey B. So horse 1 will propose to jockey B, who's unmatched and therefore accepts. Then we have one horse that's still unmatched, horse number 2, who will also propose to jockey B. And jockey B in this case is already matched to a horse that it prefers better. So because of this, jockey B, looking at its preference list, sees that 1 is preferred to 2. Jockey B will reject 2's proposal. We can see that proposals are sort of rejected one of two ways. Either it might be that the proposal was previously accepted and then discarded, as was happening before, or it could be that right out of the gate, the proposal is rejected, as just happened. Finally then, horse number 2 is going to propose to jockey C, having been rejected by A and B, and C, having not been matched yet, will accept. We're now all done. Every single horse has been matched to a jockey, and this is a stable matching. Now to pause for analysis, if each step takes constant running time in this, what's the worst case running time? In this case, if we suppose that we have n proposers and n responders, the worst case running time will be n squared. Every single proposer will propose to no more than n different possible responders over the course of its entire algorithmic running time. And because there are n different proposers, the combination will be n proposers times n proposals per proposer, or n squared. This gives us our algorithm. We are going to continue to iterate a process of finding an unmatched proposer, having them offer their next best proposal, and if it's an improvement for the responder, having that responder accept. We'll continue to do this until everything is matched. We want to argue that this algorithm is correct, that it produces a stable matching. So how do we argue this? First, parenthetically, we should conclude that this algorithm actually terminates in some finite amount of time, that we couldn't loop infinitely. And we note that the number of proposers that are matched must equal the number of responders that are matched. So, as long as there's a proposer that's unmatched, there must be at least one responder that's unmatched, which presumably means that that proposer hasn't yet proposed to that responder yet, because no responder will start being unmatched afterwards. So we know the algorithm terminates. But the question we might really want to answer is, how do we know that when it terminates, the matching is stable? Let's suppose for a moment that when we ran Gale-Shapley, we ended and found that we had some instability. That is, we had some choice of horse P and jockey R' such that P preferred R' to its current match R, and R' preferred P to its current match P'. We represent this as an instability of P and R'. What we know from P's preference order is that P must have proposed to R' first. The order that Gale-Shapley produces proposals ensures that R' would have been proposed to before R. If that's the case, then why isn't P matched to R'? It must have been that R' turned down P's proposal. If that's the case, though, we observe that that must have meant that R' turned it down for some horse that it liked potentially less than or equal to the amount that it liked P'. R''s prospects can only have gotten better over the course of the algorithm, which means that R' must prefer P' to P if it's matched to it by the end of the algorithm, which is a contradiction, as we said that R''s preferences would have been P being preferred to P' in order to produce an instability. So we arrive at a contradiction by trying to produce an instability, which means that Gale-Shapley could not produce such an instability. Another question we could ask, though, is this going to produce some single unique stable matching? This is a question truly about the problem itself. Is there always one unique stable matching for such a problem? Think about it for a moment. Can you come up with more than one way you could set up preferences on this problem, such that there could be multiple possible stable matchings? As it turns out, there's not always one unique stable matching. Let's consider the following case. On the left side, we see that horse P prefers R to R', and horse P' prefers R' to R. If we used their preferences, we would naturally have P propose to R, and P' propose to R'. And that would produce this following matching. That's what we would describe as proposer optimal. However, we could have another stable matching. This matching right here. In this case, this respects the responder's preferences. R in this case prefers P' to P, and R' prefers P to P'. However, the way that we ran Gale-Shapley usually considers proposer's preferences first. That is, we're using the ordering of the proposer's preferences in order to determine which responders will even have which proposals to consider. This means that R and R' may not even have their preferences lists looked at if P and P' quickly match to options that are distinct. How do we prove that Gale-Shapley is proposer optimal? That is, how do we prove that if some responder R is a valid match for proposer P, that is, there's some stable matching that exists such that R is matched to P, that R will never reject P? We'll set it up as follows. Let's suppose that we're looking at the first time in the progression of the Gale-Shapley algorithm that a responder rejects a valid match. We're going to say that this is R rejecting P. We're thinking about the progression of the algorithm in this case. We're imagining, by way of contradiction, that there is some first instance in which some valid match is rejected. If this rejection happened, we know that R must have rejected P for some other horse. In this case, we'll imagine P prime. So if R rejected P for some P prime, but P and R were a valid match, that must mean that there's some other version of the world in which P prime is matched to something else and P is matched to R. So the question is, who's P prime matched to in that case? We'll say it's some R prime. And we know in that particular case that that means that P prime must prefer R prime to R. Otherwise, this matching right here that we imagine, such that P and R are a valid match, would have necessarily had an instability if R was preferred to R prime by P prime. So we assume that R prime is preferred to R by P prime. And then we go back to our original setting right here, where P has been rejected by R. In order for this to have happened, P prime must be proposing to R, which means that P prime must have been rejected by R prime already, because P prime is going in order of preference. And this is an issue. It produces a contradiction, in fact, because R rejecting P was what we assumed to be the first rejection of a valid match. But in our idealized world where P was matched to R, we said that P prime was also matched to R prime. So P prime and R prime should have been a valid match as well. And that rejection of P prime by R prime must have happened before this proposal from P prime to R. What does it mean for Gale-Shapley to be proposer optimal really, though? How much worse are the responder's options going to be to the proposer's options? I've created a demonstration showing this in the case of randomly generated preference lists. You can access it right here through this Colab link, which I'll also link below. We're going to assume that there are 1,000 different proposers and responders, respectively, in our problem, and that each of them has a preference list for the other side that is completely randomized, a random list of the numbers 1 through 1,000. If we do this, and we solve this using Gale-Shapley, we find that proposers average one of their top 10 in their list, around 6.5 when I ran this. Usually, out of 1,000 different options, they're going to get an option that is very high in the list. However, responders didn't do quite so well. The average that they got for which ranking in their list was actually their final match was 136. It's a pretty significant difference in terms of ranking. Why do we care about this? If we're talking about real-world problems, like matching residents to hospitals or matching students to schools, it starts to be important who the proposers are and who the responders are. We might have said that optimality, in this case, is simply having a stable matching, that we're satisfied if there's no pair of school and student or hospital and resident who would prefer each other to the current matching that they have. However, that doesn't convey some of the subtleties of this problem. It could be that all of the schools are satisfied, but got much more of their preferences respected than the students did. And we would consider that not necessarily fair, even if it's technically stable. This was actually a significant issue, and if you look up the MATCH, the National Resident Matching Program, you'll find that in the history of the program, one of the significant changes that occurred was at one point they switched from hospitals being the proposers in the algorithm to residents. And this was a matter of fairness, something to ensure that the people who could potentially be marginalized, the residents in this case, would be able to get what they needed.